Hello, welcome to the CCC. My name is Suykerbuyk and I'm about to start my shift in the control room. In the CCC we control all the accelerators of CERN, the SPS, the pre-injectors booster, PS and LINAC, the technical infrastructure and cryogenics. But let's have a look in the LHC island where we are in stable beam mode. The stable beam mode is the most quiet period during operations, and it will give us the opportunity to explain some of the tools and displays we use during operations. Let us first have a look at the wall displays. Here we have real-time information about the cryogenics, the beam dump and injection kickers, the profile of the bunches and filled buckets circulating. This is very useful when we are filling the machine. The performance of the experiments. And we will have a closer look to the LHC page 1, which is most looked at. It informs about the accelerator and beam modes, shows mode-dependent plots, the status of the different beam flags, and the message area to inform the users, the pre-injector status, and the lifetime of the beam. Now we have a look at our so-called fixed displays. These are applications that show in real time the status of vital equipment. Every screen here shows the power supplies in one arc. Here we see the tune and orbit feedback systems, followed by the beam loss monitors, the alarms and beam interlock systems, the longitudinal bunch length, RF cavities and low-level beam control, the collimators, and the beam current transformers that show the intensity and lifetime of the beam. The stable beam period is also the best moment to update changes to our procedures that might have occurred during the previous shifts.
Start power group 95. Start power group 96.
The announcements you hear come from the LHC Announcer, a web application that translates timing events into a voice so that everybody can hear what's going on. A nice demonstration is the following. We are approaching the end of the physics film and therefore have to dump the beam. We put a message on page 1 and dump the beam.
Dump beam 1. Global postmortem. Dump beam 2. Global postmortem.
While we ramp down and pre-cycle the magnets, we use the LHC sequencer to drive all the equipment to injection settings. We have to go through a complete list. To inject the beam into the LHC, it needs more than a flip of a switch. All the pre-ejectors have to be ready and have their beams set up to meet the LHC specifications. For machine protection reasons, we are not allowed to inject a high-intensity beam into an empty machine. Therefore we start injecting a very low-intensity probe beam.
Beam mode, injection probe beam.
1, 5 hours and then the fun starts for a week. Yes, from Monday to now, okay, don't count.
Next injection, bring 1 bucket 1. Injection. Next injection, bring 2 bucket 1. Injection.
Page 1 shows that both pilots are circulating, and we see that the beam presence flag is true, and this will allow us to inject the high-intensity beam. While the SPS is loading their high-intensity cycle, we will have a closer look at the bunch profile display. We see the bunch circulating, represented by a small vertical red line. The SPS has now the correct cycle running, but we see that there is no beam because the intensity trace is flat. We will now request the beam with the injection sequencer. We will ask for beam 1 and 4 bunches. What will happen now is that the pilot bunch will be kicked out while we kick in the 4 bunches.
Next injection, bring 1 bucket 1. Injection.
On the synchrotron light monitors, we see the beam size. We will request beam 2 now and see what happens.
Next injection, bring 2 bucket 1. Injection.
We continue to fill up the machine according to a predefined injection scheme.
Next injection, bring 2 bucket 21,851. Injection.
Now that the machine is filled, we do a measurement of the beam emittance with the wire scanners.
Wire scan.
We are now ready to prepare the ramp.
Beam mode prepare ramp.
As a first step, we're going to correct the orbit with the steering program. First, we will load a reference orbit, against we will correct the actual one.
So just to show that the only difference now is...
The measured orbit is stretched out in a horizontal plot, and we can easily see that the beam is oscillating around its central orbit for beam 1 and for beam 2. To correct this, we have hundreds of corrector magnets around the ring. With the steering program, we can select the number of correctors and calculate a correction based on a magnetic computer model of the LHC. The correction seems to improve the orbit, so we send it to the power converters.
Start power group 97.
We restart the measurement and we can easily see that the oscillations have almost disappeared. When the orbit is okay, we attack tune and chromaticity. The tune viewer is the application that measures in real time the tune in the horizontal and vertical plane.
What I know is that if you're not careful with the windows, then...
For the chromaticity measurement, however, we have to make a slight radial steering in order to get the measurement. The tune viewer sends first a 5 promille negative trim, and we can see the orbit going inwards, and we see a slight tune shift. Then we make a measurement without the trim. The orbit and tune go to the initial value, and finally a positive 5 promille trim. That will make the beam go outwards, and again gives a slight tune shift. The tune viewer then calculates the chromaticity. Now that the beam measurements are done, we start to arm the equipment for the ramp. Now the tune viewer comes back into play, because this machine is used to control the feedback systems. We first switch on the orbit feedback. It prevents the orbit drifting away by sending real-time corrections to the orbit correctors around the ring. Then we switch on the tune feedback for beam 1 and for beam 2. They prevent the tunes from drifting based on peak measurements in the tune viewer window.
I know that this is that for...
Start power group 226. Start power group 96. Accelerator mode, ramp. Start collimators. Energy, 0.5 TeV and rising.
While the ramp is ongoing, we have to keep a close eye to the tune viewer window to make sure that the right peak is detected. Otherwise, we will lose the beam.
Energy, 1.5 TeV and rising. Energy.
With the synchrotron radiation monitor, we can measure the transverse beam size. For that, we use the PSRT. It's a very complicated optical system.
Energy. 2.5 TeV and rising.
It's off?
Towards the end of the ramp, the losses are going down, and therefore we see their lifetime increasing. The beam losses are measured by more than 3000 beam loss monitors placed around the ring and displayed in the BLM fixed display. Most of the losses occur in the so-called cleaning areas. In point 3, the momentum cleaning, and in point 7, the beta tone cleaning.
Energy. 3 TeV and rising.
So if you see that they're false, say attenuation setting.
The tune feedback is still going strong, and from the plot of the real-time trims, we have a good idea of the tune drift during the ramp. These trims can be fed forward into the next ramp to compensate for the drift.
Energy. 3.5 TeV and rising. Energy. Stable at 3.5 TeV. Beam mode flat top.
When we reach the flat top, we first switch off all the feedback systems. An orbit measurement shows that there is a little energy offset.
The one higher, but it
Trimming up the RF frequency with a few hertz can correct this.
And it's not much, huh? We move almost nothing.
The coupling is a little bit high. We trim it down so that we can go into the squeeze.
Beam mode squeeze. Start power group 212.
During this 20 minutes cycle, we tightly focus the beam to increase the luminosity for the experiments.
and then correct back to that.
But what I saw, in fact, I have the data for the whole field because
Alice and LHC beta star 5 meters. Atlas and CMS beta star 5 meters.
and then it follows with the offset that it was. But in fact, it's very neat.
Alice and LHC beta star 3.5 meters. Atlas and CMS beta star 3.5 meters.
With a now squeezed beam, we go into adjust mode.
Beam mode adjust.
We will now bring the beam into collision. While the separation bumps are collapsing, the experiments start to see some collisions.
Beam mode stable beams.
After declaring stable beams, the only thing that's left is IP optimizing. We are going to move the beams on micrometer level to see if we can still improve the collision rate.
Start power group 89. Start power group 90.
After 4 hours of hard work, all IPs have been optimized and there's only one thing left.